Have all of you here, and it's a pleasure to have Helene, who is a PhD student in the Quantum Tinkerer group at TU Delft, talk about our recent work on amorphous topological faces protected by continuous rotation symmetry. So, yes, you can go ahead.
All right, thanks, Daniel. So hold on, let me check everything's in order. Okay, so hello everyone. Thank you all for attending my talk today. I'm Helene Spring. I'm part of the Quantum Tinkerer group at TU Delft. And the subject of my talk is a recent work by myself, Anton Akhmerov, and Daniel Varjas. So in this work, we explored topological phases protected by average spatial symmetries in amorphous materials. And so, yes, I would like to encourage anyone who needs a clarification to unmute themselves and ask you a question, but otherwise we'll have time for also questions at the end. So I would like to start today by going over two key elements here in the title of the paper, topology and symmetry. So let me first explain what I mean by topology. Let's start by schematically visualizing a space of Hamiltonians, describing various condensed matter systems represented here by this colorful blob. So each point of this blob represents an instance of a model. And in this green region, all of the models are insulators. What we can do here is adiabatically transition between different insulating systems by tweaking parameters of the model. Now, topology, in a few words, is about things that cannot change continuously. In order to get topological, we need some other ingredient here. In our schematic, these black regions indicate gapless systems. So a transition between insulating states passing through these gapless states is not adiabatic. However, nothing stops us from circumventing these gapless areas and taking a different path. So if we want to find out what it means to be topological, a good start here would be to force our path to always go through these gapless regions. And the tool we can use to do this is symmetry. So before we see what symmetries are, let's see what they do. If a Hamiltonian has a certain symmetry, it respects a symmetry constraint. So let's focus on the Hamiltonians that respect one given symmetry constraint. It may be that only a subset of our Hamiltonians respect this constraint, and we now consider a reduced space that contains them. As a result, different insulating regions may now be completely separated by gapless regions. This symmetry-induced separation has important consequences for our insulators. And the consequence is that these newly separated insulating regions have now acquired the capacity to host special gapless modes. Since these gapless modes are created by imposing a symmetry, we call them symmetry-protected topological phases, and what was once a trivial insulator is called a topological insulator. So even though our topological insulators don't seem very insulating, since they now have gapless modes, there is a good reason why they're called that. So to illustrate this, let's look at a chunk of topological insulator embedded in a normal insulator. Where the two materials meet, we expect a transition through a gapless phase, and that's indeed where the gap closes. So the new gapless modes we saw appear aren't in the bulk of the material, but at its edges. This is a simulation of the local density of states at zero energy of a topological insulator with darker color indicating higher density. And what we see here is that the bulk is clearly insulating and that all available propagating states are at the edge. So it bears reiterating what's going on here. When going from a topological insulator to a trivial insulator, we need to have a gap closing. So topological insulators are characterized by an insulating bulk and gapless edge modes. Now that we have some idea of the part that symmetries play in realizing topological systems, let's see what symmetries actually are. So when we think of symmetries, we tend to think of spatial symmetries like reflection or rotation. In condensed matter systems, however, there are three important non-spatial symmetries. And so those are time reversal symmetry, present in non-magnetic systems, particle-hole symmetry present in all superconducting systems, and chiral symmetry present in systems with sublattice symmetry like graphene. And these symmetries, when present alone or in various combinations, serve to constrain the behavior of the system, and in doing so, create many different topological phases. And these symmetry classes form a periodic table for all topological insulators for all spatial dimensions. So throwing spatial symmetries into the mix has extended this classification. This new classification is ongoing, and case in point, this talk is actually about some new entries in this classification. Unlike non-spatial symmetries, however, spatial symmetries have an important limitation. Since a crystal only has a finite number of, for example, mirror axes, not every edge has mirror symmetry. What this means is that the topological protection by mirror symmetry is dependent on the orientation of the edge. So here's a simulation of a model hosting a topological phase protected by mirror symmetry. And we can see that the edge states, as indicated by the local density of states again, vanishes at the edge with broken mirror symmetry, and a gap has opened in the dispersion. So it would seem as though using spatial symmetries to protect a topological phase is a troublesome affair. If there was a way for us to have spatial symmetry present for all edge orientations, we wouldn't have to worry about this. Luckily for us, there is such a symmetry, but we have to go beyond crystals to find it. The idea is to consider amorphous materials. These are structures with no long-range order, and they have been found to support topological phases relying on non-spatial symmetries. But what we consider here is the use of continuous rotation symmetry, a spatial symmetry present in amorphous systems. This symmetry means that a particle traveling through an amorphous system would experience the same environment no matter what direction it takes. And thanks to this rotation symmetry, amorphous systems also support mirror symmetry for any edge orientation. And this is exactly what we wanted, a spatial symmetry present for any arbitrary edge orientation. But by now, I'm sure you're thinking, hold the phone. There's no way these messy looking random systems have any kind of symmetry. I'm not buying it. Indeed, there's something we need to say about these symmetries. They clearly aren't preserved exactly here, but they are preserved on average. So you might concede, okay, I'll believe these symmetries could be present on average, but are average symmetries good for anything in the first place? And the answer to this is yes. In 2014, the concept of adding perturbations to topological insulators was investigated. And these perturbations made it so that some of the symmetries are only preserved on average. These systems are also capable of hosting topologically protected modes and are known as statistical topological insulators. This showed that even average symmetries are good enough in the topology world. Now, where we come in is that the same idea could work for us. Even though our spatial symmetries are only average symmetries, they could still be used to create a topological phase in the form of a statistical topological insulator. Statistical topological insulators are characterized by average transmission dropping as the system size increases, as opposed to the unit transmission we're used to seeing in topological insulators with exact symmetries. So decay here is still much slower than the drop-off of transmission in a trivial insulator, which drops off exponentially with system size. So we're not talking about localized edges here. Now, the first step in creating these new proposed phases is to find a model for an amorphous system that can be protected by average mirror symmetry. And we can actually search for all such possible models for not much extra effort, if we know how to go about it. So the procedure for finding these models is the following. First, we select a symmetry class, so a certain combination of time reversal symmetry, particle symmetry, or chiral symmetry, or all three. We then select a form of mirror symmetry. And we use these to find all allowed terms of a one-dimensional Hamiltonian. Even though we're looking for two-dimensional phases, there's a reason we search for one-dimensional models here. If we can find a one-dimensional model that's ungappable, we know that once we extend the model to 2 dimensions, the one-dimensional edge will be gapped only if the two-dimensional bulk is trivial, and so not independently of the topological properties of the bulk. So we check if the one-dimensional model can be gapped. If we do see a gap, we try again with a different form of mirror symmetry and see if that's gapless. Once we find something that's gapless, we try again, and this time we don't include the mirror symmetry, and we only use the other non-spatial symmetries. The reason we do this is to check if the model is now gapped, because that indicates that mirror symmetry was necessary to protect the modes. If it stays gapless without mirror symmetry, then mirror wasn't required to protect the topological phase, which is not what we're interested in. If these conditions are fulfilled, we have a candidate model that we can extend to 2 dimensions and add rotation symmetry to. And we then repeat this process for all symmetry classes. Now, this all sounds fairly labor intensive, working all of this out, but thanks to the software package Qsim, we're able to iterate through all possibilities relatively fast. One functionality of Qsim is to take symmetry representations and work out all the allowed terms of a Hamiltonian respecting these symmetries can have, so there's no need to work it all out by hand anymore. So we now have our models, and we can go ahead and start testing in amorphous systems, right? Well, actually, before we do that, we should make sure that we do have valid models before throwing in the new element of amorphousness into the mix. It'd be better that way. And what we can do is examine the models in continuum systems first. The reason this is valid is that for small values of k, the wave number, an amorphous continuum is comparable to an isotropic continuum. What we want to do here is check whether a gap can be opened in the continuum edge dispersion by any allowed term in the model just by its mere existence. And if not, we know with some confidence that we can expect the same behavior for amorphous systems. Good news is that at this stage, we do find models that fulfill these requirements, and we're able to move forward with confidence. But the question is now that the search is finished, do we like what we see? Do we have candidates for statistical topological insulators? We can use an interesting characteristic of statistical topological insulators to check. That characteristic is that, unlike a topological insulator, a statistical topological insulator behaves kind of like an insulating bulk with a critical, disordered, lower dimensional topological insulator stapled to its edges. What this means is that we expect 2-dimensional statistical topological insulator phases to exist in symmetry classes that support not 2-dimensional topological phases, but rather in those that support 1-dimensional topological phases, which is the dimension of the edge of our 2D systems. Because of this, we expect, or at least hope, that our search returns candidates only belonging to symmetry classes where 1-dimensional topological phases are supported. So the first column, where there's an entry, and that's indeed what we see. This is a good indication that the models we found could describe statistical topological insulators. It's certainly a good sign. So we're now ready to put these models to the test in amorphous systems to see whether we can use average spatial symmetries to protect topological phases. In order to do this, we have to define Realspace models out of our Kspace models, since amorphous structures are not regular periodic structures. So we need to go to Realspace. So we go from considering the crystal momentum K to considering a Realspace quantity, the bond length D, between the sites of the amorphous system. And the way we do this conversion is by modifying symmetry representations that we supply to Qsim, and it will build our Realspace models for us as easily as it made our Kspace models. For spatial symmetries, we don't have to do anything extremely important or fundamental. The rotation or reflection is done in a different basis, but it has the same form. The non-spatial symmetries, however, are sometimes different in the continuum than in Realspace, as the sign of the bond length is not flipped, unlike the sign of the crystal momentum. This is because the hermiticity condition is also modified, where the adjoint hopping in Realspace is the reverse hopping along the same bond D. So by following the rules of this conversion, we get our Realspace models from QSIM, and we're good to go. So we're now ready to start testing our Realspace models. And the first question we have about these systems is whether or not mirror symmetry is responsible for topological protection in Realspace systems, because that's what we built them to do, and that's what we want to confirm right away. So we can confirm this or not by showing that the model is gapped on crystal edges that break mirror symmetry, and that they're gapless on every edge of an amorphous system. So we simulate segments of crystal lattices with periodic boundary conditions along two different directions, one that preserves mirror symmetry and one that doesn't. So the results show that we have gapless dispersions along the mirror preserving edge, and the edge without mirror always opens a gap for the same parameter values. So the only thing that changes is along which edge the dispersion is recorded. Now, the second part of our test involves our amorphous systems, and we expect all the edges to have average mirror symmetry, so all the edges should be protected. Right. This local density of states and spectral function simulation show that this is indeed the case. The orientation of the edge has no effect on the edge modes of the amorphous system, unlike the crystal. So it looks like we found topological phases in amorphous system protected by mirror symmetry. However, we don't yet know whether these are statistical topological insulators, which is what we expect, seeing as mirror symmetry is an average symmetry. And what we can do is, or we should do, is check whether the edges are delocalized and that we see this characteristic transport scaling of statistical topological insulators. And we check this by looking at the transport of our amorphous systems directly by simulating it. So the idea here is to record transmission through an amorphous sample as a function of system size for many different random configurations of the amorphous system. And so this is shown schematically here. What we can expect is for some configurations to yield perfect transmission, so close to 1, while others are backscattered by disorder and we have transmission close to 0. And the chances of backscattering, we expect them to increase as we increase the system size. At this stage, fitting the data is not very convenient. So what we do is we can transform the transmission data we collected into a new form, alpha, which is a quantity that is, in essence, a measure of the disorder in our systems. So replotting this data in terms of alpha, we see that we could now fit half normal distributions to histograms of the alpha statistics. So what arises from these fits is that the scale factor, proportional to the breadths of these fits, increases linearly with system size, if we have average disorder centered around 0, which is what we expect for our amorphous systems. And this behavior is what we're going to look for in our simulation data. So this is the data we collected for one of our models. So we can clearly see the half normal distribution shape of the alpha data with the half normal fit here in red. And we can also see on the right that we have fitted the square root of the fitted scale factors. And we see that they increase with the square root of the system size, which is precisely what we were expecting. We therefore have some concrete evidence that we've successfully realized amorphous statistical topological insulator phases relying on average spatial symmetries. So there's an expression that says, if it looks like a duck, swims like a duck, and quacks like a duck, then it's a duck. This looks, swims, and quacks like a statistical topological insulator. However, we don't have to stop here, as there's one more check that we can do in order to be really sure. Right. To make sure that we understand our systems, we can look at the properties of the bulk. This is so we can make sure that the topological properties of the bulk are responsible for the edge behavior, a concept called bulk edge correspondence. Without it, we cannot really claim to say that what is happening at the edge is the result of something that we understand in the bulk. To test this, we look at a bulk property called bulk invariant. So what is a bulk invariant? It is a special quantity that changes abruptly at a topological phase transition, so when the gap closes, and changes nowhere else. It's a mathematical expression constructed out of the features of a system that tells us, depending on its value when we calculate it for certain parameter choices, whether the model is in a trivial regime or in a topological regime. So it's kind of like a topological indicator. The forms of an invariant is strongly dependent on the symmetry class of the model it belongs to. So we're interested in constructing the bulk invariants in the following symmetry classes. Classes with chiral symmetry like A3, BD1, and C2 have chiral symmetry, and so their bulk invariant is a one-dimensional, in one dimensions, is a winding number. In the presence of chiral symmetry, we can rewrite a band-flattened Hamiltonian Q into a block off-diagonal form. And the winding number n then measures how much the phase of the determinant of one of these blocks changes in a closed loop around the Brillouin zone. This number is always quantized and corresponds to the number of protected propagating modes at the edge of a system going in the same direction. For a trivial system, this number is 0, because we don't expect any protected modes at the edge. What we find here when we calculate it is that it's also 0. So either our system is trivial or we haven't found the right invariant yet. So we know that we don't only have chiral symmetry, but also mirror symmetry. And in the presence of mirror symmetry, we can further reduce these small Q blocks into reflection even and reflection odd sectors. And these blocks are what we use to calculate our invariants. So we associate a mirror winding number to each mirror sector, and we find that each of these is equal and opposite to the winding number of the other sector. And so it explains why our total winding number was 0, because yeah, they canceled each other out. Class D3 also has chiral symmetry, but if mirror and chiral symmetry anti-commutes, the invariant is tied directly to the two-dimensional D3 strong invariant. If they do commute, its invariant is constructed from the invariant of the other chiral models in a modified form. I won't go over it now. For class D, the situation is similar. The invariant we choose is the mirror resolved version of the class D one-dimensional invariant. Once again, each mirror sector has its own invariant, and it's not important which one we choose. We only need to look at one of them to probe the topology of our systems. So you may notice that these invariants are written in terms of the Kspace Hamiltonians, whereas we're interested in simulating the invariants for our Realspace amorphous systems. So we have to go back to Kspace, but not simply this time by supplying the Kspace symmetry representations to QSim. What we have to do, or what we do this time, is use the Green's function. So we obtain an effective Kspace Hamiltonian from the inverse of an effective Green's function. And this effective Green's function is obtained by projecting the Green's function of the original Realspace Hamiltonian onto plane wave states. This effective Hamiltonian encapsulates the properties of our amorphous systems while still transforming in the same way as our Kspace Hamiltonians. And importantly, its gap only closes when the gap of the original Realspace Hamiltonian closes. So since changes in the bulk invariants only occur at bulk gap closings, we can thus use this effective Hamiltonian with some satisfaction to simulate the bulk invariants for amorphous systems. So here are the results of our simulations for the bulk invariants. For class D, we see here the momentum resolve spectral function of the original Realspace bulk Hamiltonian, which gives some idea of where the states are, kind of like a dispersion relation, but for a finite amorphous sample. And overlaid in red, we see the spectrum of the effective Hamiltonian, and note that the gap closes at the same point as expected. We also note that we have one crossing at k equals 0 and one at k equals infinity for different values of the chemical potential. These are points in Kspace that are invariant with respect to continuous rotation symmetry as well as mirror symmetry. At these crossings, the bulk gap is closed, and we see that our invariant at the bottom on the third row switches precisely at these points. All values of chemical potential in between correspond to the topological regime. The transport data we saw earlier was precisely for this model, and we collected it at a value of the chemical potential that is within this topological regime. So this is strong evidence for a bulk edge correspondence. We also see similar behavior for the other classes. Here we see the spectra of the effective Hamiltonian as a function of chemical potential for several values of k between 0 and infinity, and the corresponding quantized values of the bulk invariant switching as expected at the gap closings. So these bulk invariants tell us not only that we indeed have topologically protected systems, but that these are statistical topological insulators due to the connection between their invariants and the one-dimensional invariants of the corresponding class. So now we're finally satisfied and our work here is done. To sum up what we've seen here today, I'll leave you with an analogy that I thought of. So I don't know how many of you are familiar with the story Pet Sematary by Stephen King. In this story, the cat of the protagonist has a tragic accident and dies. The cat is then resurrected, which is great, but something in its behavior has definitely changed for the worse. For us, we started with a topological insulator whose edge modes are unable to survive at an arbitrary edge, but they can be brought back by adding disorder to the system, which drives the edge to a critical phase. But we've had to sacrifice something in order to get this protection back. What's happened is that we retrieved protection at all edge orientations, but had to compromise on the quality of this protection, except that it will only work out on average, and see transmission drop with system size. With that, I would like to thank you all for your attention, and would love to hear your questions if you have any. Thank you.
Thank you. Are there any questions?
May I ask one?
Sure.
Yes, please go ahead.
So hi, I'm about maybe to set on my phone, but I don't know. Okay, so you should be able to see me. My question was about your transport. I mean, when you compute the transport coefficient in your system, is it configuration averaged or not, or just on a single realization of the lattice?
You mean the transport results?
Yes.
Yeah, this was done for many different configurations. Okay. So as I mentioned, hold on, let me just reconfigure my screen share. 1 second, please. Okay, this is still going on. So we can move around better. Okay, so as I mentioned in this slide, let me just maximize this so everyone can see. All of these points represent like one sample from one particular amorphous configuration for one system size. And then we do this for a bunch of times for each system size. Because otherwise, what we would get as a result is either extremely low transmission or extremely high transmission. And so this scaling relation that we see is only valid as a measure of the average transport in the system, not for each amorphous configuration is going to give something like this.
Okay, thank you.
Sure. Oops, don't look at my notes.
I would have a question.
Yep.
Yeah, this is Björn Spirsky from Berkeley. Can you go to the slide where you describe the bulk invariants? Yeah, so those are 1D invariants, but so K should just be a number, not a vector in 2D, but you're dealing with 2D systems. So you take an arbitrary cut, or
that's right. So what we do is set one of the components of the K vector to 0, for example, and then perform the integral on a line from 0 to infinity that is mirror invariant.
Is there any problems with choosing infinity? Or
no, yeah, infinity is also a mirror invariant point, so you could also choose K equals infinity.
Like numerically, you're dealing with finite systems.
Yeah, okay, so you caught me. So instead of infinity, we just have a very, very big number, like 10 to the 16 or something, what NumPy can handle basically. So, but it works out. It works out.
Okay. And one more question. So I haven't fully understood the role of mirror symmetry, because on this slide, the table that you show on the left does know nothing about mirror symmetry, right? This is just the one entry in the Altland-Sirnbauer classification. And somehow you used mirror symmetry as a vehicle, but at the end it's not essential, or I missed something?
Well, okay, so in 2 dimensions, so as we mentioned for these statistical topological insulators, you need an average symmetry, and you need it to also be present at the edge. So what happens in 2 dimensions is that rotation symmetry is broken at the edge, and so it's insufficient to have rotation symmetry be the average symmetry. So what we thought of instead is to include mirror symmetry, which is stabilized everywhere by the continuous rotation symmetry, and it will be present everywhere at the edge. So it serves to create the right environment for a statistical topological insulator. And it all ends up working out by creating these mirror sectors that we then find a valid invariant for as well.
But can you argue that's the only symmetry for which the construction works, or?
No, yeah, for sure. So here we wanted to use spatial symmetries, so we didn't have to worry about adding statistical non-spatial symmetries, which would also change the class of the symmetry class. But if you could think of any average spatial symmetry at the edge, I think you would have to just find a new bulk invariant that is suited to that spatial symmetry. Off the top, there aren't 10 million spatial symmetries that you can use either, so I think this was definitely the simplest one.
Right.
See, Daniel has unmuted himself, so maybe he wants to add something.
In fact, like in 1D, mirror is the only spatial symmetry.
Yeah, not inversion. Well, yeah, it ends up being inversion, right?
Yeah, it's the same in 1D.
Okay, in 1D, yeah.
Right. Thank you.
I have a question, if nobody has.
Yep.
So thank you for the talk, by the way. It's quite nice. So I was wondering what happens when you like slowly break the continuous rotation symmetry. Have you ever checked the nature of the edge states?
So like, your idea would be to go from an amorphous system and then gradually remove the disorder until you end up with a crystal?
Yeah, exactly. So is there like a degree of, you say average symmetry, but is there a degree of breaking of the continuous rotation symmetry such that it destroys the edge states? Or is there an energy scale associated with it?
Well, continuous rotation was the vehicle to enable mirror symmetry to be present at all edges. So if what you do is you take like a straight edge, either aligned with X or Y, and do that process, then the states would not be destroyed. But the invariant actually does change. So hold on, let me see. I have an extra slide for this somewhere. So for continuum systems, you have you can have Z invariants, which means they can take the value like from negative integers, positive integers. But for statistical topological insulators, all you can have is a Z2 invariant, which means it's like a light switch, it's either 0 or 1. So the reason for this is in a continuum, you can have several pairs of counter-propagating modes stabilized. You can have an even number, you can have an odd number of them. But when you add disorder, only systems, only an odd number of counter-propagating modes survive. So I could imagine a situation where you start with a non-disordered environment, and maybe you have several pairs of counter-propagating edge modes. And once you add disorder, the effect of that would be just to reduce the number of counter-propagating pairs. But apart from that, I can't think of any much more surprising things happening just by manipulating the degree of continuous rotation symmetry.
Yes,
maybe I'm lacking imagination, that's all.
Yeah, I also think that if you break the continuous rotations, like depending on whether or not you have the mirror symmetry left over for that specific edge, it can gap out if the mirror symmetry for that edge orientation is gone, or stay gapless if you still have the mirror symmetry, because the edge protection really only relies on the mirror for that specific edge orientation.
So you mean, like, what you mean is then continuous rotation symmetry can be broken, so it doesn't matter as long as the mirror symmetry is there for a given edge?
Yes.
For a given edge.
Yeah, okay, I see. Yeah, okay, that makes sense. Yeah, thanks.
Hey, do we have more questions? If not, I would like to thank Helene again, and thank you all for attending this very nice talk.